See. Okay, let's see if I can. Okay, so we are recording. So today we are going to see a little more about the public key cryptography. We already made an important introduction, but I'm going to talk about it a little more. So the public key cryptography have been something that is significant. It's maybe one of the more significant advances in the last 3,000 years in the history of cryptography. So remember that each user have two keys, a public key and a private key. And we call it asymmetric cryptography because we have two keys. We don't use the same key to encrypt and decrypt. So we will use the public key, as they say here. The public key, we can share it. We have to share it, sorry. We will use it to encrypt message that other people, when they want to send a message to me and they want to encrypt it, they have to use my public key. And when I sign a message and they want to verify my signature, they have to use my public key. Now, my private key, when I'm going to use my private key, when I want so let's say that I receive a message and it was encrypted by the sender using my public key. So in this case, I'm going to use my private key to decrypt the message. And if I want to sign a document to do a digital signature, I use my private key to sign the document. As you can see, they have different functions, no? So if you look, I only use my private key. I always use my private key. I never use my public key. I share my public key with other people. So I use my private key to sign. And I use my private key to decrypt a message that they sent to me, and they encrypt it with my public key. Now, what other will do with my public key? So let's say that I sign a message with my private key. They will use my public key to verify my signature and to be sure that I signed the message. And let's say that they want to send me a message and they want to encrypt it before they send it to me. They will use my public key. So the other people always use my public key. Of course, they do not have my private key. I do not share my private key. I have to keep my private key very secret. If at one point my private key have been copied by somebody else, I have to change my pair of keys. I cannot keep using the same keys because the person can do whatever he wants with this key. So, so here they say with the public key, the person that want to send me an encrypted message will encrypt it and will verify my signature, as we say. And with the private key, I will sign or I will decrypt message that I received, no? So let's see this drawing. Let's see, this is the size of Bob, and this is the size of Alice. Let's say that Bob wants to send a message to Alice and he wants to encrypt it. So Bob, of course, have its own private key, and it's the public key of Bob, he give it to Alice. Oh no, here, I'm sorry. Bob want to send a private message to Alice. So Bob have the public key of Alice. And Bob is going to use the public key of Alice to encrypt the message. So this message will go in the internet, which is unsecure. People can make copy. We will see that they cannot do anything. When it's arrived to Alice, Alice will use her private key to decrypt the message. Remember that what we encrypt with the public key, we decrypt it with the private key. So what happens if a hacker copied the message that Bob has sent to Alice? the hacker do not have the private key of Alice. So the hacker cannot decrypt the message that Bob sent to Alice. This is the idea. So as you can see here, Bob have the private key of Alice, but have the private key of all the coworker or the friend. So when Bob want to write a message to Ted, and he want the message to be private, Bob will use the public key of Ted. So Bob have a keyring, and in the keyring he have the public key of all his friend or co-worker. So the public key rely on two keys. So the key are generated in that way. It is computationally infeasible to find the decryption key if you have the public key. If I have the public key, I cannot find, or it's very difficult, it will take many years to find the private key. We know that it is there, but we don't have the computing power. So it has to be computationally easy to encrypt or decrypt message when you have the correct key. So when you encrypt, remember that you encrypt with the public key of the person that you want to send the message. And when you decrypt with your private key, because they sent you a message that is encrypted with your public key, so you will decrypt it with your private key. So normally, the keys are related. So to tell you the truth, what you encrypt with one key, you decrypt it with the other key. Now, when we use it, when we encrypt, we always encrypt with the public key. And we decrypt, we always decrypt with the private key. When we sign, we always sign with the private key. And the person that verified the signature of the document that you have signed will use your public key to verify the signature, no? So let's see this. Here we have Alice, and here we have Bob. And Alice wants to send a message to Bob. So Alice have a private key. KR is for key, R for private, the second letter of private. And Alice have a public key. KU, K for key, U public, the second letter of public. So Alice have a private key and a public key. And the public key, she share it with everybody. So she share it with Bob. Bob also have its public key, KUB is the public key of Bob, and KRB is the private key of Bob. So of course, Bob shares its public key. So Alice have the public key of Bob. So let's see what we can do. Here, for example, we have a plain text. Alice used a private key, R for private, remember, to encrypt the message. If she do that, what she is looking for, what do you think? If she encrypt with a private key the message, is she looking for privacy? Is she looking for authentication? What do you think? If I use my private key to encrypt the message that I want to send, I'm looking for? Yeah, so I'm looking for authentication because I'm signing the message. So what happened is that I use my private key. Who can have this private key? Only me. If I am Alice, only Alice can have the private key. So she's signed. So encrypting with a private key is signing the message. Doesn't mean that if she just send it like that, what will happen? The people that anybody in the internet that have the public key of Alice can decrypt the message. And when they decrypt the message and see that the message makes sense, they say it was signed by Alice. So they just can verify that it was signed by Alice, but there is no privacy if she just encrypted with her private key. She just signed, and so this is my signature. So that have been emitted by me. So tomorrow I cannot say I didn't sign it because it have been signed by my private key. Now she take the result and she encrypted with the public key of Bob. You see the public key of Bob? She have a copy of it. She encrypted with the public key of Bob. So what she is looking by encrypting it with the public key of Bob, the result. She's looking for privacy. Nobody in the world will be able to understand this message except Bob. Why? Because Bob have the private key. So look, this was encrypted with the public key of Bob. To decrypt it, what do I need? I need the private key of Bob. Who have the private key of Bob? Only Bob. So Bob will be able to decrypt because she encrypt with the public key of Bob. So only Bob can decrypt. And after Bob decrypt, it will have something that is not really the plain text message, because the plain text message have been encrypted with the private key of Alice. But Bob have the public key of Alice. So Bob will decrypt the message, and when he will see that the message that he got makes sense to him, he will say, this message has been signed by Alice. So by doing that, we do double encryption. We encrypt with our private key to sign the message. So it's authentication. And we encrypt with the public key of the destination for privacy. So only the destination have the public key. Here have the private key that correspond to the public key that we use to encrypt. So the destination will be able to decrypt the message. And then let's say that there is two levels of decryption, because here also we decrypt, but everybody can decrypt this level because everybody have the public key of Alice. Okay, so at the end I do two encryptions, but one encryption is to sign and the other encryption is to ensure privacy, to be sure that only Bob can decrypt this message. Nobody else in the world can decrypt this message. You understand that? Okay, so there are several algorithms for public key cryptography. So the one of reverse Shamir Adelman that is called RSA is the most popular. But we have another one that is called El Gamal that is also very popular. It is based on the logarithm and the exponential function. While the RSA algorithm is based on multiplication and factorization. So multiplication is very easy to do. Factorization is very difficult to do. So with RSA, we support both encryption by using the public key of the destination and digital signature by using our private key. So look, it is based on the fact that factoring a big number is very hard. So here they recommend to use a key of 512. I would say this is obsolete now. People use key of 2048. Or yeah, 2048 is the key that they recommend now. For example, a company like Bank of America will use a 2048 key because it's have a lot of clients and want to rely on something that is very safe. But for a person, maybe 1024 bit is enough. Okay. So the plain text that you want to encrypt have to be smaller than the key. Okay, so we already saw that when we use RSA, we need two prime number that we will multiply. So I'm not going to go over those slides. So I'm going to start my virtual machine. And we are going to see how we generate a pair of public and private key. We are going to see that we can have them in different formats. We are going to see how we encrypt them. We encrypt with the public key. And how we decrypt with the private key. So oh, I don't put it here. Oh, I forgot the way for me to connect the USB drive. Does somebody have a USB-C to USB-A converter? No? So, okay, I need to send that by email. I'll come back. Okay, I wish this tool have a possibility to pause the recording, but I don't think it has the possibility to pause the recording, unfortunately. Okay. So Open and Secure Shell have a lot of tools to work with RSA. We are going to see some of them today because in lab 3, sorry, you have to work with Open Secure Shell. So let me create a directory where we are going to work. So let me call it RSA, reverse Shami Adelman. I'm going to first generate a private key. So in this document, I have a lot of information. And here, for example, I have the information of how to create a private key. So when you want to create a private key, you use this command of Open and Secure Shell. So up to now in this directory, I have nothing. As you can see, I just created a directory and I went inside the directory with the change directory command, the CD command. So I'm going to create a key and it will be a private key. Let me call it Eric private dot key. And I want maybe not that much bits, maybe just 512 bits. So we don't deal with very big numbers and we can do a nice practice. So I'm going to hit enter and it generates a private key. So remember, that we have a public exponent. It just informed me that the public exponent that it choose is this number, 65,537. So now if I look in my directory, I do have the private key. Let me show you the content of the private key. This is the private key. So the private key have been encoded base 64. So you know what is encoding base 64 because you did lab 2. Why we use encoding base 64? Who can give me an idea? When we want to encrypt a binary file, we want to have a result as a text file. So for example, this key, not the private key, of course, but let's say that it was the public key. I can just post it in my web page and people can get my public key in my web page. And it's not a binary file, it's a text file. So it's why we use base 64. And when we use base 64, you remember that we use the lowercase letter, the uppercase letter, the digit, the slash and the dot. So you will see slash and dot here. Okay, I don't see any dot. Maybe it was not necessary here to encode the private key. So when I want to see what is inside my private key, I have this command, no? Before we do that, this is the private key. Let me generate from my private key my public key. So the command to generate the public key from the private key is this command that we have here. So as you can see, we use Open Secure Shell. We use the command RSA, reverse Sharmiri Adelman. We say what is the key that we are entering. So the key is the private key. So the file is called eric-private.key. And we want to generate as an output, we want to generate the public key. So here I have the option -pub out, saying that I want to generate a public key. And here we are going to put the name as eric-public.key. Okay, I just generate my public key. So now I have my public and private key. So this public key, I can share it. So look, by default, look at the right. You see the right? What does a R here mean? That the people that belong to the group Eric can read the file. And what this R mean? That all the other user can read the file because it's the public key. I don't care that they get a copy of my public key. Look at the private key by default. Look at the rights. You see there is only a R for who? For Eric. The user Eric can read it. Nobody else. Because we don't have a R here and we don't have a R here. Which means that I don't want other people to see my private key. So let me show you the content of my public key. And as you will see, it is also encoded in base 64. This is my public key. So what do you know that we have in the public key? Because we have been working with that and talking about it for some days. What should we see in the public key? You remember the public key is two integers, the modulus and the public exponent, the modulus n, which is the product of two big prime number and the public exponent. The public exponent is 65,537. So there is a way that I can tell Open Secure Shell, please show me the content of my public key in a way that I can see it easily. So to see the content of a public key, you use this command. So let me copy it first and then we comment about it. So we use Open Secure Shell and we also use the command RSA for reverse Shamil Aderman. So we say that as an input, I'm going to give my public key. So Eric public key. And I want see in a text, I want to see the result. So look at the result. It says, you remember when I generate my public key, I say I want a public key of 512 bits. This is n, the modulus. And this is e, the public exponent. So e is 65,537. So this means that there is an integer. And this integer is the product of two prime numbers that are big. Okay? So if I ask you, I would like to have the value of this integer in decimal. How can we do that? Give me some command. Now that you are familiar with Linux, give me some command to have that integer in decimal. So let me first echo the public the modulus. So look at the modulus start here. This is the first line. Continue here. So the screen is not big enough to represent it on only one line. So secure open SSL, split it in several lines so we can see it easily, no? But as you can see, I just copy it here. And this is the integer. And as you can see, the integer is separated by, each byte is separated by colon. So how do I remove the colon? You see, I did an echo and I see the value. So how do I remove the colon here? I want to remove the colon. What can I do? So yeah, I can use stream editor. So pipe, which means the output of this command, I wanted to pass it to the stream editor. So if I use the stream editor, what can I write? So S for substitute the semicolon with nothing in a global way. So you have it here. Another way that I could have done it is what? With the tr command. You remember the tr command, the translate command? I can use the tr command, translate tr, dash delete the colon. So here is the integer. So if I want to put this integer in Python, what can I do? I want to put this integer in Python. So let me call Python tree. And I want to call modulus this integer. So here I have the integer, so I can copy it. So how do I tell Python, which is an infinite precision calculator, this is an integer that is not in decimal, but in hexadecimal? You have to precede the integer with 0x, isn't it? You know that? You know that in C and C++ also. So now if I ask to show the content of modulus, this is the integer in decimal. So I could also continue here and say, why don't you show me the integer in decimal? We already have the integer. I want it in decimal. What can we do? So basic calculator have a way to convert to another base. So let's say that I have an hexadecimal number and I want to convert it in base 10. So look at what I do. Output base is equal to 10. And for example, I say convert A0 in base 10. A0 will be, oh, sorry, input base I have to do. So input base equals 16. This is what I have to do. So if I do A0 is 16 times 10. Okay, if I put, for example, let's put 100, it will be 256. Okay, 100 in hexadecimal is 256. So what can I do here? when you use this, you cannot write the number in lowercase. The hexadecimal number, you cannot write it in lowercase. Look, I'm going to try to write AA in lowercase, and it will show me a 0. Now, if I write AA in uppercase, it show me 170. So when I write an hexadecimal number, I have to use uppercase letters. So what should I do here? To continue with my exercise and to show the number in, so I was here. Yeah, maybe I was here doing the command. Yeah, here is the command. So how do I continue here? So first I will need to do what? To translate the lowercase in uppercase. Do you agree I just put the range AF? Why? Because in the hexadecimal, we just use the letter from A to F. I don't have to do AZ to AZ. Okay, and if you look, of course, the number, which is this number, only have letters that are between A and F because it's an hexadecimal number. So here I have the hexadecimal number in capital letter. Now, what can I do? I need to pass that to BC. But before I pass it to BC, I need to say to BC what? I need to say that the input base will be 16. So I can do xarg. So echo input base equals 16. Semicolon. And then I pass that to BC. Look at this number. This number should be the number that Python just showed me. So let's see if we find the window of Python. So look at them. So BC will show this number. Let me try to put them together. So now you can compare them. Here it is what Python is showing as the modulus. And here it is the modulus that I got without using Python, as you can see, using basic command of the operating system. So as you can see, it's the same number. This is the modulus. So of course, if you use the command factor, it will not be able to factorize that. This is too big. So let's try it. I'm going to do factor here. Try to factorize this big number. It's too large. Okay, and 512 is not that big. Now, of course, in the private key, we will have it. So look what I'm going to say. Now, I'm going to say, show me the information of the private key. Information that I can see easily. So let's see if we find the command here. Okay, we don't have the command. Oh, it was here. So here, I'm going to use this time the private key. So since by default, when you put a key, open SSL, assume the private key, you don't have to say that the key is the private. It will be by default the private key. Look at the private key. So in the private key, let's see what we have. We have the modulus, and of course it's the same one. We have the public exponent. But we have the private exponent, because the private key really is the private exponent and the modulus. And look at, we have the first prime number and the second prime number. We have both numbers. So here in the private key, we have P and Q. So let me try to do the same thing that we did with the here. We put the number in decimal. Let me put the first number in decimal, which is P, the first prime number. So here we have the first prime number. So let me copy it. This is the first line. Let me copy the second line of the first prime number. Let me copy the last line of the first prime number. and we get this number. So look at what I'm going to do in Python. I'm going to say that P, which is the first prime number, I'm going to copy it from here. So it doesn't fit in one line. So BC show this part, and I have this part. So what should I verify? If I want Q, what can I write in Python? We have the modulus and we have P. How do I get Q? What is the modulus by definition? Is a product of the two prime number. So if I write modulus divided by P, I should get Q. Well, why show it like that? Okay, that should be Q. We are going to verify it. So look at, here we have the second prime number. So I'm going to ask to convert that to a decimal number to see. So here I have my formula that do everything for me. So I'm just going to replace the first number, which was the first prime number, with the second prime number. So this is the first line, then the second line, then the third line of the second prime number, which is Q. And look at what we get. Let's compare it. Let me clean here and compare it. Look at this number with this one that we get here. You see that it's the same one? So I can say Q is equal modulus divided by P. So now, as you can see, the private key have a little more information that we would be expecting. We will be expecting just the modulus and the private exponent, which is there. We'll not expect more, but as you can see, it have the two prime number. And it have the public exponent also. So we don't need all this information for the private key, but having all this information make it faster when we have to compute, for example, when we are going to sign or when we are going to decrypt. It makes it faster. So it's why in the private key we have all this information. Okay, so let's see now how we put the public key in another format. So we have two formats, very common. The format that we are using here is called PEM format, P-E-M. So the PEM format can be sent by email, for example, or can be posted in a web page. You can post your public key in your web page. This is just the person see it in your web page, just select it, make an edit copy, and can use it in his computer, for example, to encrypt and send you something or to verify your signature, because we will use it, other people will use it to encrypt, to send something to you or to verify your signature. So this is the PEM format. There is another format that is called the DARE format, which is the binary format. So how do we get the DARE format? So let me show you. I'm going to copy this key in something that I will call temp key. I'm going to remove from the file temp key the first and last line. So look at, we have the first line that say this is the public key. This is a public key. And we have the last line here that say this is the end of the public key. I want to remove this, the first line, and remove the last line. What can we do here? to remove the first line, for example. We have many commands that we can use. We can use the stream editor if we want. So if I use sed have an option, which is, for example, one delete. One delete means remove the first line. So look, you see the first line that say begin public key is not there anymore. We have the second, third, and fourth line of the public key. If I want to remove the last line, I can do that. Dollar means the last line. Look, so let me escape the dollar. Yeah, I have to escape the dollar. So as you can see, we have the first line, the second line, and the third line, but we don't have the last line anymore. So if I want to remove both, what can I do with the sed editor? I can apply the sed editor 2 times. So I can say remove the last line and then remove the first line. 1D. One is line number 1. I want to delete it. D is for delete. And we have the 2 lines that are in between, which is the base 64. So now that I remove these 2 lines, I want to decode, because it have been the public key have been encoding with the base 64 tool. I want to decode it. What should I do here to decode it? You have been using this tool in homework number 2. What can we do? Yeah, yeah, it is base 64 encoded. So I want to decode it. Exactly. So base 64-D. What will happen that it will show me something that I don't understand, because it will be a binary file. So look, this is something that I don't understand, but this is the key in binary. So let me save it as Eric public key, and let's put the dash binary. Oh, this is their format. Maybe I put there. Okay, this is the key in binary. How can I see the key in binary? Because if I try to cut the key in binary, I will see something that I don't understand, because it's a binary file. Look at what it did. How can I see it as an hexadecimal string? What can we do here? Yeah, so XXD, and look at it, it is there. This is the content of my public key. So inside I should find the 2 integers, the public exponent and the modulus. So let's find them out. So for example, I have the modulus in Python. So if I type modulus, it will show me the modulus in, by default, base 10. How do I say I want to see the modulus in hexadecimal? How do I say Python, show me this modulus in hexadecimal? So there is the hex command that will transform an integer to a hexadecimal string. This is it, the modulus in hexadecimal. So this, I should find this inside this file. So I don't know if you see it. Try to see it and let me know if you see it, because the modulus is there. So look here. Let me start here up to here. This is the modulus. So let's see. So it starts with 0, 0. Of course, Python will not show 0, 0 that are not significant. So there is a 0, 0, then a C6. You see the C6? Then the 5, 5, the E9, the 5, 5, the E9, blah, 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 blah. And it ends with 1, 1, AB, E1. 1, 1, AB, E1. So you see, In the binary, we do have the modulus. And where is the public exponent? The public exponent is 65,537. So let me tell Python I want to have 65,537. I want to have it in binary, in hexadecimal. So look at the public exponent is here. You see it? So of course the zero that is not significant, Python don't show it. So 0, 1, 0, 0, 0, 1, 0, 1, 0, 0, 0, 1. It is there. So you see, mostly this file have very little information but the two integer, the modulus and the public exponent. And of course, I can do the same thing with the private key and find also inside the modulus. I will find the public exponent, the private exponent, the first prime number and the second prime number. They are all inside also. Is it okay? So now I can say, oh, very good. How do I use the public key? Let's say that I give my public key. Eric gives his public key to you. And you want to encrypt a message and send it to Eric. So let's say that we have a message that say hello. How can I generate a file that only have inside hello, which is 1, 2, 3, 4, 5 characters? So echo, hello. Okay, let's call it 5 plain. What happened here, it will put one more thing inside. It will go to the next line. So it will not have 1, 2, 3, 4, 5 characters, it will have 6 characters. So look, if I look at inside, let me do XXD. So it say it have H, which is 48 in hexadecimal, E, which is 45, L, 46, 4C again for the other L, O, and go to the next line. I don't want this go to the next line, for example. Let's say that I want to suppress it. If I just want hello, how can I do? -N. Now, if you look at my file, we just have L. So we have 1, 2, 3, 4, 5 characters. Let's say that this file, I want to encrypt it using the public key of Eric. So who will do that? Somebody that want to send something to Eric and want to be sure that the message will be private. You want to send this hello and you want to be sure that nobody understands this hello. So this person, of course, will have the public key of Eric. When it's arrived, Eric will decrypt it with its private key. Okay? So you can do both. You can encrypt with the private key and decrypt with the public key, or encrypt with the public key and decrypt with the private key. Now, encrypting with the private key is when you want to sign. So let's say that I'm going to encrypt with my private key. I have my private key here. If I encrypt it with my private key, I just want to be sure that when I send it to the internet to you, I don't mind that people can decrypt it. I just want to show that this message was written by me. So there is a command to encrypt. And in this case, what we are going to do, if we use this command, we are going to sign, really. So okay, let's do first this one, to encrypt using the public key. So let's come back to the first idea that I have. Let's say that you are another user. You have the public key of Eric and you want to encrypt this file and to be sure that when you send it to Eric, only Eric can decrypt it. So you have the public key of Eric. So how do you encrypt the message? First of all, when we encrypt, we need to have a block of 512 bits. Why we need a block of 512 bits? Because the key of Eric are 512 bits. So the RSA algorithm will take a block of the same size of the key and will encrypt it with the public key. So first we need to bring this block to 512 bits. So how many bits this block have? The file have for now. How many bits are inside? So we have 5 bytes. Hello is 5 bytes. So how many bits we have? 5 times 8, 40 bits. This file has 40 bits, isn't it? How do I put a command to know, for example, the size of this file in bytes first? What can I do? Word count dash character. Count the number of characters in this file. 5. Okay, I want to get rid of because it's telling me in the first column the number of bytes, and in the second column it tells me the name of the file. I want to get rid of the name of the file. What can I do here to get just the first column? So there is a cut command, no? Cut dash field. I want the first field. And the delimiter is a space. So look at, we have the 5. Now, how can we multiply this 5 by 8? Because a byte is 8 bits. What should I do here? So let me echo. I need to do 8 times. If I do 8 times, it will show me 8 times. I need to put 8 times on the result of this output. I need to put it after the time. How do I do that? I use the XR command. The XR command put the result of the previous command at the end. So look at 8 times 5. You see it? And what should I do now that I have 8 times 5? I send it to the BC command. 40 bits. So any file that you give me, it will give me the number of bits. Okay, how do I extend this file to 512 bits? How many bytes I need to insert in the file? So I need to know how many bytes are in 512 bits. So 512 divided by 8 will be what? 64, isn't it? I need 64 bytes, and I have 5 bytes. So I need to insert how many bytes? 59. I need to insert 59 bytes. So what I want to do is to insert 59 bytes in 0 at the beginning of the file. So let me show you the file again. So instead of having the first byte to be 48, which is a H, I want 00, 00, 00, 00, 59 times. So I need to insert at the beginning 00, 00, 59 times. So how can I do that? So there are many ways to do it. There is a command that is called dd. This command works like that. You've put input file. So I'm going to say there is a 0 file that generates only 0. And then I put output file. Let me generate a file that is called padding. Padding of 59 bytes. .bin. So here I can say what is the block size. So the block size will be 1 character. And how many times I want to write a 0, I want to do it 59 times. So look at this command. The input file is a file that already exists in the system and that generates 0. The output file is the name that I choose, padding of 59 bytes.bin. So the block size is 1 character, 1C is 1 character. And I want to put this block size 59 times inside the file. So now if I look, I should have this file generated. It is there. Look at its size, 59. And if I look its content, look at 59.0 inside. You see? I could generate a file with 59.0 inside, 59 bytes, and all the bytes are 0. So there is, if you want random bytes, if you want to generate a file with random byte, there is, instead of /dev/0, there is a file that is called /dev/mu-random. So let me do it, for example, again, but this time I'm going to use mu-random. Mu-random, and let's create a file erase.bin. So we remember to erase it. So look at, now I have a new file that is called erase.bin. It has 59 bytes. And if I look at its content inside, it will be a random content, because this dev/urandom generates random bytes. Now, if I tell you, okay, I want a file with 59 bytes, and I want 59 capital A inside. What can you do? So in Python, how you generate, for example, I can use Python. So I can do, for example, 59 times A. You see it? And then this, I edit, copy it, and put it in a file. So how can I do, for example, what can I do is I edit, copy it here. So I'm pretty sure, because Python, I told Python 59, and I do an echo -n. I put this string that I copy, I paste it, and let me copy it in the same file, the erase bin. Now, if I look, the erase bin has 59 bytes, as you can see. And if I look inside this file, it has 414141 59 times, because I want A, capital A, 59 times inside. So you see how we generate file as we want. So, okay, let me remove this file. So now that we have the two files that we are need, this one has 59 bytes, and this one have 5 bytes. So I want to generate a file that will start with the content of this one and have this as the final part. So I will have 59.00, and then the last 6 bytes or 5 bytes will be hello. The last 5 bytes will be hello. How can I do that? So I can use the concat command. So I say first I need the padding, then I need this content, and let me generate a file that I call result.plaintext. .plain. So look, I generate a new file, which is result.plain, and it has 64 bytes. This is exactly what I want. And of course, What we want in this file, inside this file, is at the beginning 5900, as you can see, and then at the end 5 bytes that correspond to hello. You see how I did the file? So now I want to encrypt. So when you want to encrypt with the public key of somebody, the command is this command. Let me copy it and we comment about the command, because you will be using this command in the lab that you are doing now. So let me pass the command and let's see. So we use OpenSSL again. So there is a subcommand or a command of OpenSSL, which is reverse Shamir Ademan utility. The utility allows me to encrypt, decrypt. So in this case, I want to encrypt. And I want to say that the padding, I did it by hand. It's a raw padding. I added 0 at the beginning. So to encrypt, I'm going to use the public key of Eric because I want to send Eric a private message that say hello. So let me say that the key will be the public key of Eric. The file that I want to encrypt is, I call it result.plain. And the output will be result.cipher. Okay, it is encrypted. So it will also be a file that has 64 bytes. So if you look at result.cipher, it also has 64 bytes. I can look inside. This is result encoding with the public key of Eric. I wish I should say this is 00000059 time and result at the end encoding with the public key of Eric. So now I would like you to prove that what we see here using Python is the encryption of hello with the public key of Eric. So let me go back to Python. So in Python, we have the modulus. What else we need? We have the modulus. We need the public exponent. So the public exponent is to encrypt. You remember? Is 65,537. So now we should be able to encrypt hello with the public key of Eric. Do you remember what is the formula that we need to use? Let's say that M is the plain text. So we are going to put hello. How do I put hello here? So hello is an integer. So let me show you. The message is in which file? Is in the file that is called file.plain. So this hello is an integer. So let me copy it. And let me put it here. But I'm going to, of course, say that it is in hexadecimal. So if I want to see it in decimal, this is hello in decimal. How do I encrypt hello? Who can tell me what should I write here to encrypt hello? So this is in the slides and we have been talking about it. We did some exercise also. We have to do what? M to the power of the public exponent modulus modulus, isn't it? Look at this integer. You see this integer? Let me show you the content of the file that we got after we encrypt it. So this is in hexadecimal and this is in decimal. So let me put it in hexadecimal also. So one way to put it in hexadecimal is with the hex function. Look at it. So look at, in Python, say start with 65, 65, 6D, 6D. Then we have 85, 85, C8, C8. Let me take two. A0, 0E, A0, 0E. You see it? And if I take the last two bytes, 6777, 6777. So you see, we show that we use a tool that do a lot of work for us in the background, but we know what the tool is doing because we know all the theory that is behind. So using a basic tool like Python, we were able to, if we take the plain text hello, we were able to see that hello is encrypted like this hexadecimal string, which is this one that we have in the ciphertext. So look, now I'm going to remove the file result.plain, which have the hello. Before I remove it, let me show you. It's just have the hello inside. Okay, a bunch of spaces, a bunch of 00 on the hello. I should have used this tool. So a bunch of 00 on hello. So I'm going to remove this file. So we don't have this file anymore. Let me show you the content. So we just have the file that is called result.cipher. Let me also remove the original file, file.plain. So we don't have any file that say hello, except this one, which is encrypted with the public key of Eric. So you send this file to Eric, just the file. And Eric wants to decrypt the file. So there is a command in OpenSSL, which is this command, that use also the RSA utility. So look at the command. OpenSSL is the command RSA utility of OpenSSL. We are going to decrypt. We are going to say that the file that we are going to pass, the padding was doing by row padding. So Eric needs his private key to decrypt. So here we are going to put the private key of Eric. Only Eric has his private key. So the file is the cipher file. So it's called result.cipher. And the output will be the plain text file that I already removed. It will be result.plain. So this file, we don't have it. So I'm decrypting. And now let's see the content of the file result.plain. It should be back to 5900 on hello at the end. Look at it. So now if we do it with Python. So look at what I'm going to do. This is the ciphertext. This is the ciphertext in hexadecimal, in decimal, sorry. And this is the ciphertext in hexadecimal. So if I want to decrypt the ciphertext, now I give you the integer that correspond to the ciphertext. How do you go back to the plain text? You should do what? So C to the power of the private exponent. We need the private exponent that we call normally D. So we don't have the private exponent. It is in the private key of Eric. Let me show you the private exponent again. So we are going to use the command OpenSSL, RSA. So the input will be the private key of Eric. And we want to show it in text in the screen. Look at the private exponent. It is there. So this private exponent, I'm going to put it in Python. So before I put it in Python, let me remove all the column. So I copy the first line. Here it is, edit copy, edit paste. I'm going to copy the second line. So here I copy the second line. I'm going to copy the third line. I copy it. The fourth line. So as you can see, D is big on the last line of D, of the private exponent. Okay, so this is D. So let me put that in Python. Because of course, if you want to decrypt, you need to have the private key, and the private key have the private exponent. So let me copy the second line of D and paste it here. And let me copy the last line of D and copy it here. Okay, so we have D. Now we have D. I can check D. It is there. How do I go? Now I have the ciphertext, which is this integer. How do I go back to hello? What should I do? So C to the power of the private exponent modulus modulus. Okay, it's going to take a long time maybe. So I better use another tool that do the same thing. So there is a power function that have 3 parameters. You put the first parameter, the second parameter, and the last parameter. So you are going to do C to the power of D, modulus modulus. And look at what it gives me. And this integer is M. As you can see, it's the same one. So I can show that the decryption come back to hello. Hello in decimal is this. This is hello in decimal as an integer. Okay, do you have any question? No? Okay, so I want to introduce now what is called a digital certificate. Have you heard about a digital certificate? Have you heard about that? I'm pretty sure you heard about it. Where did you heard about digital certificates? Yeah?
Or digital certificates, the locks that are on the HTTPS.
Okay, so with the HTTPS, we use digital certificate. We use this, which means that when you access Amazon, Amazon did generate a public and private key. And the problem of let's compare a little the private encryption algorithm with the public encryption algorithm. In the private encryption algorithm, you have one key. So the sender and the receiver have to share the key. What is the problem of sharing a key? You need to agree on a key. So sometimes it's not easy to agree on a key because you don't see the people. You don't see the people with frequently. So it's not easy to, if I see you every day, as I was telling you, maybe we have lunch every day, we can agree a key because we have lunch every day together. But otherwise, let's say that I work here and you work in New York, it's not easy for me to agree a key, a common key between us. So what is the benefit of the public key cryptography? That I generate my pair of key and I distribute my public key. So you may say, oh, okay, you want to communicate with somebody in New York. So you need to give this person in New York your public key. What about if a hacker is between you and the person that is in New York? And when you try to pass your public key, this hacker pass a key that belongs to him, a public key that belongs to him. This can happen. This is called a man-in-the-middle attack because it is between me and the person that is in New York, my coworker in New York. And I want to send my public key to my coworker, and this person that is in the middle intercept the communication, remove my public key, put his public key, and send it to the person in New York. So at the end, this person will have a conversation. This hacker will have a conversation with the person in New York. So we can have a problem of the distribution of the public key. So what we did is that we developed something that is called the public key infrastructure, where we have certification authority. And those certification authority will generate what we call digital certificate. So a digital certificate is a digital document that contains my public key and is a safe way to distribute my public key. Because I was telling you, the problem is when I send my public key to the person that is in New York, maybe a hacker in between us change the key and put his key. So I need a safe way to distribute my public key. And everybody can verify, oh, this is really the public key of Eric. So we'll do that through certification authority. So we have several certification authority in the US that are very important. Can you give me some names? Have you heard about DigiCert, Global Cert, Entrust, Let's Encrypt, GoDaddy, Microsoft, Google, certification authority also. Of course, they are less known as certification authority because they are known. For example, Google is known for its web browser and for its search engine. Microsoft is known for the software that it produces, the operating system and the Office. But those companies are known as certification authority, root certification authority. So there are several of them in the world. In the US, I will say that here I put a list of them that are important. Let me see. So VeriSign, DigiCert, Global Sign, Entrust, Let's Encrypt. Yeah, this is the one that I just mentioned, are the important certification authority. So what is a digital certificate? I was telling you it's a digital document that allow me to distribute my public key in a secure way. So people can say, yes, this is the public key of Eric, because there is a way to verify that this key that I receive on an email is really the public key of Eric. So the email have not been intercepted and they change the public key of Eric. It's really the public key of Eric. Or when you connect with HTTPS to Amazon, you want to be sure that you connect to Amazon. So there is a way to verify that. And we need to talk about the digital certificates. So I'm going to say, what is a digital certificate? I already gave a first definition, but what is inside a digital certificate? So we will have this inside a digital certificate. So it is defined in a request for comment, which is the request for comment 5280. So the first field that we will see is the version of the digital certificate. They call them also X509 certificate or SSL certificate for secure socket layer certificate, no? So the first thing that we will see is the version number. Then in a certificate, we have a serial number. So the authentication authority, every time that it emits a new certificate, it uses a different serial number. So if there is a problem, let's say that there is a certificate that was emitted by DigiCert. DigiCert will ask you, what is the serial number? So you give the serial number and that identify only one certificate that was emitted by DigiCert. So the serial number, every time that DigiCert emits a new certificate, it has to use a different serial number. Then the certificate is signed by the authority, the certification authority. So to sign it, you remember how we sign? if I want to sign, what can I do? So I use my private key and I encrypt. This is one way. Another way is the one that we just saw. We use our private key and we encrypt. So everybody have my public key. I send this message, the person use my public key, decrypt, and if this message makes sense to this person, it was encrypted with my private key. So this person is sure that this message was emitted by me because it decrypted with my public key. So what will do this the certification authority to sign the certificate? It will first do a digital fingerprint using one algorithm. So there are many algorithms, we have discussed them already. MD5 is an algorithm. SHA-1 is another algorithm. The most common used algorithm is SHA-256. So they will use probably SHA-256 to get a digital fingerprint, and then they will encrypt it with their private key. The certification authority will encrypt this digital signature, this digital fingerprint with its private key. Okay, then what other field we have? We have the issuer. The issuer is who emit the certificate and who sign the certificate. So it will be, for example, DigiCert, or it will be Global Cert, or it will be Let Us Encrypt. So we'll see that the issuer will have several fields. For example, C for country, S for state, L for location, O for organization, OU for organization unit, and CN for common name. Then the certificate have a validity period. So we'll have a valid from when we can start using the certificate. It will have a date and a time, and valid to. So the certificate will be valid from this date and time to this date and time. So the valid to is also a date and time in the future. So the subject is to whom we emit the certificate. So the issuer will be DigiCert. And DigiCert emits a certificate, for example, for JSU. DigiCert signed the public key of the JSU. So this is the owner of the certificate. So for example, in country here, we will put USA. In state, we will put Alabama. In location, we will put Jacksonville. In organization, we'll put Jacksonville State University. In organization unit, we might put nothing, which means it's cover all JSU. Now, if we want a certificate for MCIS, in organization unit, we will put MCIS. But if we want the same certificate for all JSU, in organization unit, we don't put anything. And in common name, we'll put the domain name, jsu.edu. If we want to cover all JSU, we can put star.jsu.edu. So that star.jsu.edu will cover, for example, cs.jsu.edu or math.jsu.edu or MCIS, which exists really, .jsu.edu. So it will cover anything .jsu.edu, star, okay? So then you will have the public key. So in the digital certificate that DigiCert is going to do for JSU, we will have the public key of JSU. Why? Because JSU needs a digital certificate to distribute its public key in a secure way. So people can verify when they receive the public key of JSU inside the certificate that it really belongs to JSU. There is a way to verify it. So the subject alternative name. Let's say that JSU have another business that is called, for example, teaching.online. And JSU want to use the same certificate for teaching.online. So in subject alternative name, it can put another DNS name or a series of DNS name. Then we will have the policy. So there are different types of certificate. We will see that next time. So we have certificates that are domain validated. We have other certificates that are organization validated. And we have certificates that are extended validated. So domain validated, the certification authority do very little validation. It just validates the domain. Organization and validated, it verifies the domain, but also ask the business to provide some document of creation, document emitted either by the state of Alabama or the union. So they do verify that the business exists, that the business have a physical address. I don't know, you see a lot of web page in the internet where they sell, they don't even have the physical address. So you have to be very careful with those pages, web pages that sell very cheap, of course. So they attract you. They might be scammer because they don't have a digital certificate, or if they have a digital certificate, they went through a deep validation. And there is an even more deeper validation, which is extended validated. Extended validated means that someone of the digital certification authority go to the business physically, investigate the business. So this is a very high level of investigation that is done on the business. So you are much sure that the business exists, is not a scammer, because the people, somebody of the certification authority went there, see that it's legal, that it doesn't have big issue. I mean, for example, that somebody didn't sue the business is not in big problem. Otherwise, if the business is in big problem, they are not going to give it an extended validation. Extended validation means that I did investigate the business a lot, and I can tell you this business is serious. Okay, there another field that is called CRL, Certificate Revocation List. So you may have your certificate. Let's say that I am JSU or I'm Amazon. I have a certificate. At one point, hacker break into my system, steal my private key. So what should I do? I need to revoke my certificate. I need to tell DigiCert, hey DigiCert, you remember I asked you to sign this public key for me? So this public key, unfortunately, I have a problem. They got the private key associated. So I need to revoke it. So nobody use it. So they create a list with serial numbers where they put the serial number of all the certificates that have been revoked. So the certificate revocation list is a way that you can revoke your certificate because it has been compromised, no? So in the past, they used to use this CRL, the certification revocation list, but today they use a protocol that is called OCPS, Online Certification Status Protocol, which is better, as we will see. Then we have a field that is called key usage. Why can you use this digital certificate? So possible value are for digital signature, for example, key encipherment, data encipherment, certificate signing, certificate revocation list signing. So this is the possible use. And we have an extended key usage, because when they did this usage, this field at the beginning, they only consider 8 value. And then they did extension to the certificate to consider more values. So here we have more value, to say what the certificate can be used for. Okay, so I think it's time. So we are going to, yeah, it's time. We are going to stop here, and on Thursday we will continue with digital certificate, and we will see them. So you understand why you have this padlock, it's called, this padlock in the URL of the browser when you connect to Amazon. So you are sure that you are Amazon, and Amazon need to be sure that you are Eric Games. So you need double authentication. You want to be sure that you connect to Amazon, and Amazon will be sure that you are the legitimate Eric Games. It's not the same way that Amazon identify us, that we will identify and be sure that we are connecting to Amazon. Okay, I'm going to stop recording, and I see you in 2 days.